Welcome class. This is Professor Ravikumar. We will explore relativistic quantum mechanics by deriving and analyzing the foundational Klein-Gordon and Dirac equations. We will break down their continuity equations, unpack the math behind Dirac matrices, and formulate the equations in their covariant forms. Finally, we will apply these theoretical frameworks practically, such as using the Klein-Gordon equation to understand the energy levels of the hydrogen atom.
Today we're diving headfirst into one of the absolute most fascinating sagas in the history of modern physics. We're going all the way back to the 1920s, a time when physicists were really grappling with the two biggest heavyweights in the scientific world, Einstein's theory of special relativity on one hand, and the completely bizarre, newly born world of quantum mechanics on the other. Our story today actually follows a mathematical protagonist on a massive quest to unite these two huge theories. We are tracing the wild story of the Klein-Gordon Equation, which is this brilliantly beautiful but deeply, deeply flawed mathematical hero.
Okay, let's dive right into this. At the time, physicists had a major mystery on their hands. Schrödinger's famous equation was, fantastic at describing quantum waves, but it had a really glaring weakness. It literally only worked for particles moving at relatively slow speeds. It completely ignored Einstein's rules of special relativity. So the ultimate challenge in 1926 was pretty obvious. What happens if you actually try to combine Einstein's relativistic energy-momentum relation with quantum wave mechanics? The race was completely on to find a single, unified equation.
Section 1. Marrying quantum and relativity. To really understand how physicists tried to force this marriage between relativity and quantum mechanics, we've got to take a look at the math they started with.
So the initial goal actually seemed simple enough, right? Just take Einstein's energy equation for a free point particle and swap in the standard quantum operators for energy and momentum. But immediately they hit a massive mathematical roadblock. Take a look at that square root. Put in quantum derivative operators under a square root expands into an absolute nightmare, like an infinite non-local mess of all powers of the derivative operator. And worse, it leads to a theory where space and time coordinates appear in a completely unsymmetrical form, which just totally ruins the elegance that relativity demands.
So how do you get out of this deadlock? Well, you use a really clever mathematical trick. Instead of dealing with the square root, step 1 is to just square the entire equation right from the start. You get e squared equals c squared p squared plus m naught squared c to the fourth. It's brilliant because by squaring it, you dodge the square root trap entirely. And then, only then, do you actually substitute in your quantum operators.
And when you do that, the math starts to look incredibly elegant. A lot of that is thanks to that intimidating little box symbol right there, the D'Alembertian operator. It's this beautifully neat package that combines both spatial derivatives, that's your del squared, and the time derivatives. Because it packages space and time together in a very specific, unified way, using this operator guarantees what physicists call Lorentz covariance. Basically, that means the equation holds up perfectly under the strict rules of special relativity.
And that leads us to this beautifully perfect covariant triumph, the Klein-Gordon equation, suggested in 1926 by physicists Klein, Fock, and Gordon. By the way, the k in that equation is just a constant based on rest mass and the speed of light. At first glance, this looked exactly like the relativistic replacement for the Schrödinger equation that absolutely everyone was searching for.
Section 2. The negative probability crisis. But, as it turns out, our hero equation harbored a dark secret. By using that clever trick of squaring the energy at the very beginning, physicists had inadvertently invited total mathematical chaos into their universe.
The core of the problem becomes really clear when we compare it directly to the standard Schrödinger equation. Notice the stark contrast here. The Schrödinger equation is a first-order differential equation in time, but the Klein-Gordon equation, specifically because of that D'Alembertian operator we just talked about, is second-order in time. That means to actually solve it, you need to specify both the initial position of the wave function and its initial rate of change over time. And that completely breaks the conventional probability interpretation of a single particle wave function in standard quantum mechanics.
So, being second order in time led to two absolute catastrophes. First, by squaring the energy, they introduced extraneous negative energy solutions, which meant sacrificing positive definite energy. Second, and honestly even more bizarrely, when you try to calculate the probability density of a particle, meaning the literal chance of finding the particle in a specific location, the formula can actually spit out negative numbers. I mean, just think about the sheer absurdity of that. How can you possibly have a less than zero chance of finding a particle?
Now, what's really interesting here is that the source text explicitly confirms this. The occurrence of that negative probability density
is entirely due to the presence of those pesky time derivatives in the expression. To avoid this mathematical nonsense, you simply can't allow any time derivative other than the first order to appear. Because of this, the Klein-Gordon equation completely and utterly fails as a standard probability wave.
Section 3. Applying it to hydrogen. But hey, physicists aren't ones to just throw an incredibly elegant equation in the trash without at least kicking the tires first, right? They decided to see if this flawed equation could survive a real-world test. So they zoomed in on a tangible system, the absolute simplest atom we have, the hydrogen atom. To do this, they basically took our relativistic particle and trapped it in the electric field of a proton, introducing a Coulomb potential, V of R. Because that potential is spherically symmetric, they were able to separate the variables into a radial part, which is how far the electron is from the center, and an angular part, so they could solve for the stationary states.
And here is exactly where the equation offered a genuine glimmer of hope. When physicists looked at the non-relativistic limit, meaning when the energy of the particle is very small compared to its rest energy, so essentially we're talking low speeds, the Klein-Gordon equation perfectly reduces down to the standard Schrödinger equation in the presence of electromagnetic potentials. So, the equation wasn't total nonsense. At low speeds, it properly mirrored the familiar non-relativistic world.
Section 4. Define structure correction. But to really see if this equation was useful, they had to analyze the final energy equation that the Klein-Gordon model spit out for the hydrogen atom. And hidden inside that complex math was a brilliant victory. When you expand the energy equation using binomial series, you end up with three main terms. The first term is just the standard rest energy. The second term gives you those familiar Balmer levels of the hydrogen atom. But this brilliantly illustrates the real magic of the equation, that third term. That third term is a relativistic correction. It actually removes orbital degeneracy and correctly predicts a fine structure to each of the energy levels in hydrogen, which is something the original Schrödinger equation simply couldn't do.
Section 5. The equation's true legacy. So, despite this amazing victory with hydrogen's fine structure, the Klein-Gordon equation initially fell into complete disrepute. It couldn't accurately model electrons, because, well, electrons have spin, and there is simply no way to include polyspin matrices in this equation without destroying its invariance. It is strictly an equation for particles with zero spin.
Because of that, for a while it was totally discarded. But then came the true narrative climax. Physicists Pauli and Weisskopf looked back at this equation and realized the negative probability wasn't a bug. It was actually a feature. They were just misinterpreting what the math was trying to tell them. They realized that the density function shouldn't be interpreted as probability density, but as charge density. And since electrical charges can naturally take both positive and negative values, the negative results suddenly made perfect, beautiful sense.
The Klein-Gordon equation wasn't a failure at all. Physicists were literally just asking the math the wrong question. Once the broader theory of quantized fields was developed, the Klein-Gordon equation returned to its rightful place. Not as a single particle state equation, but as the field equation for quanta associated with spin-zero particles, perfectly accommodating systems having both signs of charges. It really leaves us with a provocative thought. How many theoretical failures in physics today are just mathematically perfect equations waiting for us to discover the unexpected reality they actually describe?
All right, let's dive right into this explainer, where we're going to demystify exactly how relativistic quantum mechanics applies to a real-world model, the hydrogen atom. We constantly hear about the theoretical wonders of quantum mechanics and the mind-bending rules of relativity, but honestly, it's pretty rare to see exactly how these two massive pillars of physics actually merge together on a piece of paper. So today, we're going to walk through the exact mathematical derivation using the Klein-Gordon equation, and we'll see exactly how it completely shapes our understanding of the simplest atom in the universe. So we have to start with a fundamental question. How do we actually transition from an abstract free-floating particle to an electron mathematically trapped in an atom's electric field? The foundational Klein-Gordon equation is absolutely fantastic for describing a free particle, one just coasting through space without a care in the world. But real physics gets interesting when particles actually interact. So how do we modify our pristine relativistic wave equation to account for an electron that is firmly caught in the electromagnetic grip of a nucleus? Well, our ultimate goal in this explainer is to walk step by step through the math to see how injecting relativity into quantum mechanics uncovers the fine structure of atomic energy levels. You see, the standard non-relativistic Schrödinger equation gives us a really great approximation of hydrogen's energy levels, but it misses some tiny, absolutely crucial details. By factoring in relativity, we're aiming to derive an equation that perfectly predicts those minute splits in energy, that fine structure, that experimentalists actually observe in the lab. Here's our quick agenda for this mathematical journey. 1. The relativistic hydrogen setup. 2. Separating the variables. 3. Solving the radial equation. 4. Deriving the energy levels. And finally 5. Unpacking the final equation. Okay, Section 1. The relativistic hydrogen setup. The initial modification here is actually surprisingly simple. We just account for the electron in the Coulomb field. In Step 1, we start with the standard Klein-Gordon equation for a free particle. Then, for Step 2, to trap our electron, we introduce the Coulomb potential, V of R, which equals negative Z E squared over R. This represents the attractive force from the nucleus. Finally, Step 3, by substituting this potential into our energy operator, essentially replacing the total energy E with E minus V of R, we combine them to form our brand new relativistic equation of motion for the electron. Now, it looks a bit daunting with its complex operators, for sure, but conceptually, we've basically just strapped an electromagnetic anchor to our free particle. Moving right along to Section 2, separating the variables. Now for a quick checkpoint. In physics, when a problem seems literally impossibly complex, we hunt for symmetries to save us from impossible math. Because the Coulomb potential of our hydrogen atom doesn't change over time, and because it's perfectly spherically symmetric, we get to use a brilliant mathematical cheat code, separating the variables. The spherical symmetry is exactly what allows us to break this massive equation into much more manageable pieces. So how do we actually go about separating the equation? Well, first we slice right off that time-dependent part by assuming the solution takes the form of a spatial function multiplied by a complex exponential of time. Simple enough. Then we take that remaining spatial function and split it again. Because of the spherical symmetry we just talked about, the angular parts perfectly resolve into standard spherical harmonics, or YLM terms. What we are left with, and really the only thing that still contains the unique fingerprint of our relativistic potential, is the core radial equation. This tells us exactly how the electron behaves as you move directly away from the nucleus. Which brings us to Section 3, solving the radial equation. This right here is a massive aha moment. Think about the standard non-relativistic Schrödinger equation. It features a classic angular momentum term, L times L plus 1. But our new relativistic Klein-Gordon radial equation? It's almost completely identical, except that angular momentum term has been slightly altered to L times L plus 1 minus gamma squared, and gamma incorporates the fine structure constant. This tiny algebraic shift is the literal mathematical footprint of relativity, and it completely changes everything about how we solve this equation. Now, to actually use this math, we have to force our solutions to behave in physical reality. In quantum mechanics, a wave function that shoots off to infinity at the center of the atom is completely useless to us. It's what physicists call, quite politely, not well behaved. So, to prevent the math from blowing up at the origin, we introduce a new variable, s, and substitute s times s plus 1 for our modified angular term. Furthermore, for the solution to remain finite, s must strictly be a non-negative number. Finally, the series solution demands that our parameters satisfy a very specific quantization condition. Lambda must equal an integer n prime plus s plus 1. This crucial step forces our continuous math into discrete, quantized steps. All right, Section 4, deriving the energy levels. Time for a serious algebraic maneuver. We take those rigorous boundary conditions we just established and substitute them into our expression for lambda. This leaves us with a pretty messy equation where the energy, E, is trapped inside a square root fraction. So to liberate it, we square both sides and carefully rearrange the terms to solve for E. Because gamma is a very small number, we can use a binomial series expansion to stretch the equation out, keeping only the most significant terms up to gamma to the power of 4. It's a heavy algebraic lift for sure, but the result is this beautiful, highly revealing formula for the energy of the hydrogen atom. And finally, Section 5, unpacking the final equation. This is the big so what moment. All of that dense algebra perfectly splits into 3 incredibly meaningful pieces. Term 1 is simply mc squared, the famous rest energy of the electron. Term 2 drops out exactly like the non-relativistic energy formula, giving us the standard Balmer levels that govern basic hydrogen spectral lines. But term 3? That is the crown jewel. It contains that gamma to the 4th power. This is the relativistic correction. It mathematically proves that relativity removes the orbital degeneracy of the atom, predicting the fine structure, that tiny splitting of energy levels that standard quantum mechanics completely misses. The math just works perfectly. But wait a second. Is it all well with the Klein-Gordon equation? Before we celebrate too hard and pack up our chalk, there's a fundamental flaw we really have to acknowledge when analyzing the probability density. Sure, we've successfully predicted the energy levels, but what does this equation actually say about the particle itself? We run straight into the probability problem. Because the energy in the Klein-Gordon equation can mathematically be negative, the traditional probability density completely breaks down. If we try to calculate the probability of finding our electron in a specific spot, the math sometimes spits out a negative percentage. And a negative probability makes absolutely zero physical sense for a position. For a while, this actually made physicists think the Klein-Gordon equation was a dead end. But it was brilliantly resolved by Wolfgang Pauli and Victor Weisskopf. They realized that if you multiply this broken probability density by the charge of the particle, it suddenly makes perfect sense as a charge density. Since electrical charge can absolutely be negative or positive, the math is completely saved. But it forced physicists to reinterpret the entire meaning of the wave function. And that leaves us with a fascinating dilemma that paved the way for modern quantum field theory. It makes us question the very nature of the particles we're trying to describe. Think about it. We started by simply trying to make an electron obey the speed of light, and we ended up proving that we can no longer think of it just as a single particle with a probability of being somewhere. We literally had to shift our view to a field of charge density. It brilliantly illustrates how pushing the limits of mathematical derivation doesn't just give us better decimal points, it fundamentally rewrites our understanding of reality. So, if relativity forces us to abandon probability for charge density in the Klein-Gordon equation, what other fundamental realities are we currently misinterpreting? Just waiting for the next mathematical correction to flip our perspective completely upside down. Welcome to the Explainer. Today, we're doing something a little different. We're going to treat theoretical physics like a grand detective story. We're on this quest for a more perfect model of the universe, and we're picking up right where some of the greatest minds in history hit a wall, just following their trail of mathematical breadcrumbs. We're looking closely at the Klein-Gordon equation and its application to the hydrogen atom, uncovering exactly how physicists pushed the boundaries of what we thought was possible. So here's our game plan for today. We'll start with the limits of Schrödinger's equation, then introduce the Klein-Gordon solution. From there, we'll apply it to the hydrogen atom, dive into the Balmer levels and fine structure, and finally, confront a massive plot twist, the negative probability flaw. I promise, we've got a clear, logical path through all this dense physics ahead. Let's get into it. Part 1. The limits of Schrödinger. Let's set the stage and look at the central problem early quantum physicists were dealing with. Right, so the Schrödinger equation, absolutely a monumental triumph. But it had this one glaring issue. It was strictly non-relativistic. I mean, it treats space and time totally unequally. You've got a first-order derivative for time, but a second-order derivative for space. And if we know anything from Einstein's special relativity, it's that space and time absolutely must be on equal footing. They demand Lorentz covariance. But if you try to just take that relativistic energy-momentum relation, E squared equals P squared C squared plus M naught squared C to the fourth, and plug it directly into a quantum operator format, you run into immediate trouble. Which brings us to part 2, the Klein-Gordon equation. This was the proposed fix, born directly out of that relativistic energy-momentum relation. So here is the crux of the issue. How do you handle that relativistic energy equation? If you try to take the square root of the energy operator, you literally end up with an infinite series of derivative operators. It creates a non-local theory that is incredibly messy and, frankly, just physically unacceptable. So what's the elegant way out of this deadlock? Well, back in 1926, Klein, Fock, and Gordon suggested something brilliantly simple. Just square the equation. By substituting the operators into the squared energy equation, they bypass that nasty square root entirely. And the result? The Klein-Gordon equation. It's a beautifully covariant form that restores symmetry, treating space and time derivatives as absolute equals. All right, part 3, applying Klein-Gordon to hydrogen. We've got our relativistic wave equation, so let's put it to the ultimate test. To actually see if this works on hydrogen, we need to follow a pretty specific mathematical path. Step 1. We drop our charged electron into the nucleus's Coulomb field. Because this field is stable and spherically symmetric, Step 2 lets us use a really neat trick to cleanly separate the time variables from the spatial ones. Then, Step 3, we isolate that radial component, basically the distance from the nucleus. And that is where we do the heavy lifting to actually solve the equation. Now, what's really interesting here is that when you write out that radial part of the equation, a tiny mathematical shift reveals some massive physical implications. It actually looks incredibly similar to Schrödinger's version, but with one huge difference. The standard angular momentum term, L times L plus 1, is slightly reduced by a factor called gamma squared. And this gamma, it incorporates the fine structure constant, which is that fundamental number describing how charged particles interact. This single, simple substitution is literally the mathematical fingerprint of relativity, altering the structure of the atom.
Moving on to part 4, Balmer levels and fine structure. This is the mathematical climax of our explainer.
Because this is where abstract algebra translates into actual magic we can measure in a lab. By solving that radial equation and expanding the energy terms out using a binomial series, we arrive at this incredibly revealing energy formula. Let's break down the 3 main pieces that pop out. First up, we get the rest energy of the electron, mc squared, totally expected in a relativistic framework, right? Second, we get the precise energy levels corresponding to the Balmer series of the hydrogen atom, which perfectly matches early quantum observations. But that third term, that is the real prize. It's a relativistic fine structure correction that depends on both the principal quantum number n and the orbital quantum number L. Basically, this brilliantly illustrates how relativity removes the orbital degeneracy that we saw in the non-relativistic model. It predicts a fine structure splitting of the hydrogen energy levels. Suddenly, energy levels that used to look identical are splitting apart. And this is something we can literally see when we measure the light from these atoms. Part 5, the negative probability flaw. Prepare yourselves, because here comes the dramatic plot twist in our little detective story. So we've successfully modeled the hydrogen atom's fine structure. High fives all around, right? Well, is it all well with the Klein-Gordon equation? Has the case been closed? As it turns out, the moment physicists looked really closely at the actual foundations of the equation, the entire structure threatened to collapse. The root of this massive problem lies in the continuity equation. Look, for any quantum wave equation to make sense physically, it absolutely must have a conserved probability density. Schrödinger's equation? It has a perfectly straightforward one that is always positive. But when you derive the continuity equation for the Klein-Gordon equation, well, because it's second order in time, the expression for probability density suddenly includes a time derivative of the wave function. And since the wave function and its time derivative can take on arbitrary values at the same time, this equation allows the so-called probability density to actually be negative. I mean, you cannot have a negative probability of finding an electron. That is just a physical absurdity. So what do you do when a beautiful equation yields an impossible result? You change your perspective. Physicists Wolfgang Pauli and Victor Weisskopf essentially rescued the math by reinterpreting it. They realized that if you just multiply this problematic density by the electrical charge, E, the negative values suddenly make perfect physical sense. It wasn't a probability density at all. It was a charge density. Because electrical charge can absolutely be positive or negative, the equation perfectly describes a system of particles that have both signs of charges, like certain mesons. But, and this is a big but, it comes with a major sacrifice. It means the Klein-Gordon equation completely fails to give the conventional probability interpretation of a single particle wave function, which leaves us with this incredible, provocative thought straight from our source text. The Klein-Gordon equation, if useful at all, does not describe the probability wave, which the Schrödinger equation does, but describes something else. It's such a powerful reminder that science is this messy, iterative, stumbling process. The Klein-Gordon equation was a brilliant leap forward. It unlocked the relativistic corrections for hydrogen, yet it ultimately broke the very definition of quantum probability for a single electron. So if this equation doesn't describe the electron's probability wave, what does? Well, that very question is exactly what forced Paul Dirac to step up and invent an entirely new equation, one that would change physics forever.
Let's jump right into this explainer and unpack one of the most brilliant, mind-bending leaps of logic in 20th century physics. We're going to explore Paul Dirac's mathematical detective story, where a single, stubborn square root completely broke our understanding of the universe, and how he ingeniously derived the relativistic wave equation to fix it.
Here is our path for today. We'll start with the quantum relativity problem, look at Dirac's bold square root, dive into the alpha-beta mystery, reveal the matrix solution, and finally end up with a positive probability.
Section 1. The Quantum Relativity Problem.
Right, so our core clue starts here, with the fundamental relativistic energy equation for a free particle. E equals plus or minus the square root of c squared p squared plus m squared c to the fourth. Honestly, it looks innocent enough, right? But having that massive square root sitting over the momentum and mass terms, that becomes a giant mathematical roadblock when you bring it into quantum mechanics.
Here's why it's such a headache. In the quantum realm, energy and momentum aren't just simple numbers. They are operators. They involve spatial derivatives. So if you trap those derivatives inside a square root, your only mathematical escape route is to expand it out into an infinite series. Just imagine trying to solve an equation that constantly spawns an endless, sprawling string of time derivatives. It creates this totally unmanageable, asymmetrical nightmare.
Now, early on, physicists working on the Klein-Gordon equation tried to sort of brute force workaround. Their logic was, well, let's just square the energy and completely obliterate that square root. Problem solved, right? Actually, no. While squaring it got rid of the root, it created a second-order differential equation in time. And when they ran the numbers, it spat out physically impossible negative probability densities. I mean, you literally cannot have a minus 20% chance of finding an electron. So Dirac looks at this messy reality of second-order equations and just flat-out rejects it. He looked back at the absolute elegance of Maxwell's equations for electromagnetism, which are strictly first-order in both space and time. He knew, in his gut, that his new equation had to mimic that exact same first-order elegance to actually work.
Section 2. Dirac's bold square root.
This is where Dirac's absolute audacity really shines. Instead of squaring the whole equation to hide from the math, he just tackled it head-on. He boldly guessed that the expression inside the root could simply be factored linearly. He hypothesized he could pull the momentum and mass terms right out of that root by introducing a brand new set of unknown variables. He called them alphas for the spatial dimensions and beta for the mass term.
Section 3. The alpha-beta mystery.
But here is the catch. For Dirac's linear, first-order guess to perfectly equal the original relativistic energy equation when you squared it back out, these new alpha and beta variables couldn't just be any old numbers. They had to follow some incredibly strict, bizarre rules. First, their squares had to perfectly equal 1. Okay? But second, and this is the weird part, they had to anti-commute in pairs. Meaning, if you multiply alpha x by alpha y, it absolutely has to equal the negative of alpha y times alpha x.
We are staring at a massive paradox here. Think about regular numbers for a second. 2 times 3 is 6, and 3 times 2 is also 6. The order simply doesn't matter. So what kind of numbers on Earth can you multiply together in reverse order and get a negative result?
Section 4. The matrix solution.
And here is the twist. Regular numbers can't do this. They just can't. Dirac realized these weird variables weren't standard numbers at all. They had to be matrices, arrays of numbers that play by totally different algebraic rules. In matrix math, A times B does not necessarily equal B times A. By tapping into anti-commuting matrices, Dirac finally found the exact mathematical key that fit his strict constraints.
Now, physicists at the time already knew about a set of anti-commuting matrices, the 3 2x2 poly-spin matrices. But remember, Dirac's equation demanded 4 variables, 3 alphas for space and 1 beta for mass. And here is the mathematical brick wall. You literally cannot find a 4th 2x2 matrix that anti-commutes with the other 3. It just doesn't exist. So Dirac was forced to creatively expand the dimensions, constructing entirely new, much larger 4x4 matrices from scratch.
Section 5. A positive probability.
So, the moment of truth. By substituting these brand new 4x4 matrices back into his initial linear guess, Dirac successfully derived it, his final relativistic Hamiltonian and wave equation for a free particle. It beautifully treats space and time on an equal footing, bringing that elegant Maxwellian first-order symmetry directly into the quantum world.
But there was an interesting side effect. Because he was now using 4x4 matrices as the operators, the quantum wave function itself had to fundamentally adapt. It couldn't just be a simple single-component scalar function anymore. It was mathematically forced to transform into a 4-column vector, which we now famously call a Dirac spinner. And it turns out this specific 4-part structure was hiding brand new physical information about the particle, specifically its intrinsic spin. Most importantly, this matrix formulation completely cured the fatal flaw of the Klein-Gordon approach. When you calculate the continuity equation using Dirac's new spinners, the math yields a strictly positive definite probability density. It finally behaved exactly the way standard quantum mechanics requires, providing a rock-solid mathematical foundation for the universe.
Okay, picture the scene. It's the early days of quantum physics, and scientists have a massive, high-stakes mystery on their hands. They're desperately trying to marry Einstein's theory of relativity with the incredibly weird new world of quantum mechanics. But the math just wasn't working. The fundamental laws of the physical universe seemed to literally be breaking down on the chalkboard. So in this explainer, we're going to act as mathematical detectives. We're looking at how one physicist, Paul Dirac, essentially cracked the code by totally redefining the mathematical reality they were working in. Let's get right into it. Here's a quick roadmap for the math we're decoding today. 1. The relativistic quantum problem. 2. Dirac's bold Hamiltonian equation. 3. The rules of the matrices. 4. The 4x4 matrix reality. And finally, spinors and quantum operators.
Starting off with Section 1, the relativistic quantum problem. Think of this as our mathematical crime scene.
Right, so the leading attempt to combine relativity in quantum mechanics back then was something called the Klein-Gordon equation. At first glance, it seemed pretty solid. It took the basic relativistic energy equation and replaced energy and momentum with operators. Standard stuff, right? But it had a fatal flaw. Because it relied on second-order time derivatives, it did something utterly nonsensical. When physicists tried to calculate the probability density of a particle, which is just the chance of finding that particle in a specific place, the equation could actually spit out a negative number. I mean, think about that. How do you fix an equation that claims a particle has a negative chance of existing? You can't exactly have a minus 20% chance of finding an electron. It's a physical impossibility.
So physics was at a total deadlock. On the one hand, you've got the Schrödinger equation. It works beautifully. It gives a perfectly functional, positive probability density, but it completely ignores Einstein's relativity. It only works in a non-relativistic limit. On the other hand, you have the Klein-Gordon equation, which does account for relativity, but completely fails to give a normal probability interpretation. It just leads to that impossible negative probability density we just talked about. They desperately needed a completely new mathematical container to break this deadlock.
That brings us to Section 2, Dirac's bold Hamiltonian equation. Enter Paul Dirac, our lead detective.
Now, Dirac was really influenced by Maxwell's equations for electromagnetism. And the thing about Maxwell's equations is they are elegant first-order equations in both space and time coordinates. Dirac looked at the mess of the Klein-Gordon model and realized the negative probability density was directly caused by those pesky second-order time derivatives. He figured, to keep relativistic invariance and ensure positive probability, the new wave equation absolutely must be strictly first order in time. But here's the catch. According to relativity, space and time are on equal footing. If it's first order in time, it has to be first order in space coordinates too. So, he made a huge, unproven mathematical leap. As the texts say, Dirac boldly wrote a new equation to basically force reality to comply.
He proposed this completely new relativistic Hamiltonian equation. E equals h equals c times alpha dot p plus beta times mc squared. You see, to get rid of the square root from the original relativistic energy equation, Dirac essentially guessed that the energy could just be written as a linear first-order equation. But for the math to actually balance out when you square it later, he had to introduce these new coefficients. Take a close look at those Greek letters, alpha and beta. They are the primary suspects in our mystery.
Moving to Section 3, Rules of the Matrices. It turns out alpha and beta have some truly bizarre mathematical fingerprints.
To make his first-order equation square perfectly back into the accepted energy-momentum relation, Dirac inadvertently placed some incredibly strict conditions on these alpha and beta coefficients. Number 1, they have to anti-commute in pairs, meaning if you multiply alpha times beta, it must equal negative beta times alpha. Number 2, the square of any of these coefficients must equal 1. Okay, hold on. Wait, what? Just think about regular numbers for a second. 2 times 3 is always exactly the same as 3 times 2. Regular numbers never ever anti-commute. This was a massive realization. It meant Dirac's alpha and beta coefficients couldn't possibly be standard numbers. They had to be complex data containers. They had to be matrices.
And because alpha and beta are matrices, they are bound by very specific matrix rules. If you use the cyclic property of traces, along with that anti-commutation rule we just covered, the math proves undeniably that the trace of these matrices must be exactly 0. So why does a trace of 0 matter so much? Well, since their squares equal unity, the eigenvalues of all 4 of our matrices, that's 3 alphas for the spatial dimensions and 1 beta, have to be plus or minus 1.
If the trace is exactly 0, it means you have a perfect balance. The number of +1 eigenvalues must perfectly equal the number of -1 eigenvalues. This acts as a hard, physical constraint. It mathematically restricts our matrices to an even dimension, so no 1x1 or 3x3 matrices allowed. They have to be 2x2, 4x4, 6x6, and so on.
Section 4, the 4x4 matrix reality. Let's look at how these strict clues forced a massive upgrade to our understanding of reality.
The good news was, physicists already had a handy set of anti-commuting matrices. The three 2x2 Pauli spin matrices, sigma x, sigma y, and sigma z. There are 3 of them. They're 2x2, which is an even dimension. Their squares equal unity, and they anti-commute beautifully. Problem solved, right? It looked like the absolute perfect fit.
Except, there was a huge problem. Our universe has 3 dimensions of space, so we need 3 alpha matrices. Sure. But remember relativity? It connects space and time, bringing in mass and rest energy. That requires the beta matrix. We need a 4th matrix. And as the math makes perfectly clear, finding a 4th matrix that anti-commutes with the 3 Pauli matrices inside a 2x2 dimension is mathematically impossible. A 2x2 mathematical container just isn't big enough.
And here is the climax of our investigation. Since 2x2 was out, what's the next possible even dimension? 4. Dirac was literally forced by the laws of mathematics to invent a 4x4 matrix reality. He arbitrarily set the beta matrix to be diagonal, giving it 2 + 1 and 2 - 1 eigenvalues, and from there he easily found the 3 other 4x4 alpha matrices that anti-commute with it. These are the specific 4x4 matrix representations for alpha x, alpha y, alpha z, and beta. By doing this, he fundamentally expanded the framework we use to calculate the reality of quantum particles.
Finally, Section 5, Spinors and Quantum Operators. How does this new 4x4 reality ripple out to the rest of quantum mechanics?
Well, the consequences were sweeping. The quantum wave function, usually denoted as psi, which describes the state of the particle, couldn't just be a simple scalar function anymore. It had to evolve. It became a 4-column vector, functioning alongside its conjugate transpose, psi dagger. And to be clear, these aren't your standard 4 vectors from relativity. They have completely unique transformation properties. Today, we call them Dirac spinors.
And the upgrades keep coming. To make sure the math stayed perfectly consistent across the board, the counterparts to standard Schrödinger operators in Dirac's theory had to expand as well. Even fundamental, basic operators like position x and momentum px now have to be represented as 4x4 diagonal matrices. Dirac's simple demand for a first-order equation completely re-architected the mathematics of quantum physics.
But the absolute greatest twist in this whole story comes right at the very end. Yes, Dirac solved the probability problem. His 4x4 matrices guaranteed a positive definite probability density. But this new math still allowed for negative energy solutions. Only this time, instead of throwing them out as some weird mathematical glitch, Dirac trusted his 4x4 reality. He asked a profound question: what does negative energy actually mean for our physical universe? Answering that directly led to the stunning, world-changing theoretical discovery of antimatter, the positron, a particle with the same mass as an electron but an opposite charge. All of that came from simply demanding that a mathematical equation be beautiful, first-order, and logically consistent. It's just incredible stuff.
Hey everyone, and welcome to this explainer. Today, we're going to take a journey through what I honestly think is one of the most beautiful transformations in all of theoretical physics. We're looking at Paul Dirac's absolutely legendary relativistic equation for a free particle. Now, Dirac was a literal genius, right? And his original equation was this massive breakthrough because it successfully merged quantum mechanics with special relativity. But mathematically speaking, well, it started out kind of clunky. So our objective today is to take that initial equation and give it a complete symmetrical mathematical makeover. We're going to see exactly how physicists repackage this vital formula into a form that's just as aesthetically stunning as it is physically profound. Let's dive in.
So here is our quick roadmap for the makeover. First up, we'll look at the symmetry problem. Second, the beta multiplier. Third, we'll enter the gamma matrices. Fourth, defining spacetime 4 vectors. And finally, number 5, we'll reveal the final covariant form. All right, starting right off with section 1, the symmetry problem. Basically, a flaw in the original design. To really understand why a makeover was even necessary, we have to look at the original equation. You can literally spot the asymmetry right there in equation 1. Notice how the time derivative, the part with dt on the left side, is completely isolated. Meanwhile, all the space derivatives are just clustered together over on the right side. Now, in special relativity, space and time are supposed to be treated on completely equal footing, right? They're interwoven parts of a single fabric we call space-time. But here, they're totally separated, practically sitting on opposite sides of the fence. To get true relativistic invariance, we absolutely need this equation to reflect that equality between space and time.
So how exactly do we fix it? Well, here is our 4-step makeover plan. Step 1, we start with that asymmetrical free particle equation. Step 2, we multiply it by a specific factor containing the beta matrix, just to reorganize the terms a bit. Step 3, we define a brand new set of matrices called gamma matrices to package up all the messy bits. And step 4, we apply 4 vector coordinates to perfectly fuse space and time together. This is our blueprint, and it's going to get us to perfectly symmetrical Lorentz covariance without getting completely lost in the weeds of the math.
Okay, moving right along to section 2, the beta multiplier. It's time to reorganize those terms. Check out how just a simple multiplication completely reorganizes the landscape of the equation. By multiplying Dirac's original equation by a factor involving the beta matrix, specifically beta over c times each bar, we managed to shift all our derivatives, both space and time, over to the exact same side. And that gives us equation 2. We've successfully grouped the spatial derivatives into that summation from k equals 1 to 3. It's a huge step forward, because space and time are finally hanging out on the same side. But, look at those coefficients sitting in front of the spatial derivatives. I mean, mathematically, sure, it's valid, but visually, it's incredibly messy.
Which brings us perfectly to section 3. Enter the gamma matrices. Time to package up those messy bits. Since equation 2 was looking pretty cluttered, physicists realized they needed a clever packaging technique. Take a look at equation 2a. Instead of writing out that super clunky combination of matrices every single time, they just wrapped it all neatly into a single brand new symbol, the gamma matrix. It's like taking all your loose cables and putting a zip tie on them. So much cleaner.
Let's actually take a quick cognitive breather here and let the definition of this new tool sink in. We're defining a set of 4 gamma matrices. The first 3, gamma k, where k is 1, 2, and 3, handle the spatial components. They're defined exactly as -I times beta times alpha k. Now the fourth one, gamma 4, handles the time component, and that one is simply defined as the beta matrix itself. By creating this new matched set of 4 matrices, we're laying the absolute perfect groundwork to match the 4 dimensions of space-time.
All right, section 4, defining space-time 4 vectors. Let's officially merge space and time.
So we fixed the matrix coefficients, but our actual coordinates, x, y, z for space and t for time, are still kind of lopsided. We need to formally merge them, and we do this by treating time as a spatial dimension, literally introducing an imaginary time coordinate x4, which is defined as I times c times t. Guys, this is the critical key to locking in relativistic symmetry. Grouping the 3 spatial dimensions with this new imaginary time dimension creates one unified 4-component vector. Space-time is no longer fragmented. It is a single cohesive entity denoted by a subscript mu that runs from 1 to 4.
And here is how that physically builds our actual equation. In equations 3 and 3a, we swap our new 4-vector coordinates right in. Instead of having a summation from 1 to 3 for space, and then a totally separate term just awkwardly hanging off the end for time, we elegantly consolidate them. Space and time derivatives are now perfectly integrated into one seamless mathematical operation. Just look at that single summation from mu equals 1 to 4. Beautiful, right? Okay, so we've got our perfectly packaged gamma matrices. We've got our beautifully unified space-time 4 vectors. So what actually happens when we combine them together in the covariant formulation practice? This is it. This is the exact moment we've been building toward.
Section 5, the final covariant form, the grand finale.
Boom. Here it is. This is where all of our mathematical repackaging, substituting, and defining pays off spectacularly. Look at equation 4b. Gamma mu times the partial derivative with respect to x mu plus mc over h bar all acting on the wave function psi equals 0. I mean, look at how incredibly sleek this is. The summation sign is just gone. It's actually implied by the repeated mu index. Space and time derivatives are perfectly unified under this covariant notation. It completely, 100% resolves the clunky asymmetry we started with.
Let's really appreciate what we just did by looking at a before and after side by side.
On the left, we've got Dirac's original free particle equation. It's bulky, the time derivative is totally separated from the space derivatives, the matrices are scattered everywhere. Now look over to the right, the covariant form. It is sleek, perfectly symmetrical, and incredibly compact. Keep in mind, the physics hasn't actually changed at all. This still describes the exact same quantum phenomena, but the language we're using to describe it, it has evolved to reflect the true unified nature of the universe.
Now, you might be asking, why does this mathematical makeover actually matter? Well, expressing the equation in this covariant form guarantees something absolutely vital. It makes Dirac's equation relativistically invariant. If the state vector transforms under a Lorentz transformation in this exact prescribed way, it means the laws of physics hold perfectly true, and they look exactly the same no matter what constant speed an observer happens to be traveling at. The mathematical beauty here is literally the ultimate proof of its physical robustness.
We took a brilliant but messy equation and uncovered the absolute symmetry just hiding beneath the surface. And honestly, it leaves us with a pretty profound question to ponder. Does nature inherently favor mathematical elegance and absolute symmetry? When our equations become this beautiful, are we simply inventing better notation, or are we actually getting closer to reading the true underlying source code of the universe? It's a fascinating thought to leave you with.
Okay, let's dive right into this explainer and explore how Paul Dirac solved one of the absolute biggest crises in early quantum mechanics, the problem of negative probability. It's a fascinating journey of mathematical correction and profound physical insight that literally changed how we view the universe forever.
So before Dirac came along, physicists were relying on the Klein-Gordon equation to try and describe relativistic particles, but it had a fatal flaw. It failed because its mathematics allowed for completely impossible negative probabilities. So how exactly do you fix a mathematical crime against physics? I mean, a probability of finding a particle that is less than 0, that makes absolutely no sense in the real world.
To see how we pulled it off, let's quickly run through our agenda. We're looking at 1. Dirac's wave equation, 2. the Hermitian conjugate, 3. the continuity equation, 4. probability and current density, 5. the non-relativistic limit, and 6. normalization and expectation. We're going to trace Dirac's exact mathematical path, moving logically from his foundational wave equation right through the creation of its mathematical mirror, all the way to proving that probability is perfectly preserved over time. Section 1. Dirac's wave equation. Fixing Klein-Gordon's flaw. Let's start with the baseline of this whole mathematical mystery. The crucial point to understand here is that Klein-Gordon's inclusion of a second-order time derivative inherently allowed probability density to dip below 0. Which, as we just established, is physically impossible. Dirac realized the only way around this was to demand a wave equation that contained exclusively first-order derivatives in time. And to satisfy the strict laws of special relativity, if it's first order in time, it absolutely has to be first order in space coordinates too. What you're seeing here is Dirac's incredibly elegant solution. Notice how it utilizes only first-order derivatives in time and space. By doing this, he built a completely new foundation for relativistic quantum mechanics. He essentially made a massive leap and replaced the standard squared momentum and energy operators with these entirely new mysterious alpha and beta components, all just to make the math work perfectly. Section 2, the Hermitian conjugate, creating the mathematical mirror. To build a foolproof rule for probability, Dirac needed a counterpart to his new equation. This is where we apply the Hermitian property to those alpha and beta matrices. See that dagger symbol on the psi wave function? That indicates the adjoint. The fundamental, unbreakable rule here is that you have to reverse the order of factors in the matrix product upon conjugation. Doing this creates a perfect mathematical mirror image of the original equation, which sets us up for the next crucial phase of the derivation.
Section 3. The continuity equation, building the conservation law. Now that we have our primary equation and its conjugate mirror, it's time to combine them.
Think of this like a mathematical recipe to build a strict conservation law. We can break this complex manipulation into 3 really logical actions. First, you multiply the original equation by the adjoint wave function on the left. Second, you multiply the conjugate equation by the original wave function on the right. And third, you simply subtract one result from the other. The direct result of those 3 steps is what we have right here. And by subtracting those 2 modified equations, something really beautiful happens. The clunky terms containing the mass-energy components, those beta mc squared terms, they perfectly cancel each other out. This resulting formula is the immediate precursor to our final, elegant conservation law, isolating the relationship between time derivatives and spatial gradients. Section 4. Probability and current density, redefining physical reality.
Let's step back from the pure algebra for a second and define the actual physical meaning hidden inside this dense math. By defining probability density exactly like this, as capital P equals psi dagger times psi, Dirac mathematically guaranteed that the probability would always be a positive definite physical reality. Because it relies on the sum of the absolute squares of the wave function's components, it completely wipes out the absurd negative values that plagued the flawed Klein-Gordon model. Similarly, we have probability current density, represented by a lowercase j, which equals c times c dagger times alpha times psi. This represents the actual physical flow of this positive probability. You can sort of think of it acting like a fluid current. It ensures we can accurately track the movement of our quantum particle through space, basically guaranteeing that no probability just vanishes into thin air. This anchors our entire derivation. It's the ultimate continuity equation, definitively linking the probability density and current we just defined. It tells us that the partial derivative of p with respect to time plus the divergence of j equals 0. So what does that actually mean for us? Physically, it means if the chance of finding a particle in one specific spot goes down, it's only because that probability flowed somewhere else. Section 5. The non-relativistic limit. Connecting back to classical quantum mechanics. A true test of any new relativistic theory is whether it neatly collapses back into familiar rules when things are moving slowly. When we look at the relativistic probability current, obviously we see it requires 4-component Dirac spinors and those highly complex alpha matrices. But when we strip away the high relativistic speeds, Dirac's complex probability current density perfectly cleanly reduces to the familiar classical framework you'd expect from the standard non-relativistic Schrödinger equation. As explicitly noted in the math here, the expression for P retains the exact same form as the non-relativistic one. This is huge because it proves Dirac's radical, matrix-heavy math perfectly bridges the gap between high-speed relativistic environments and classical, slower-moving quantum mechanics. He didn't break the old physics at all. He seamlessly expanded it. Section 6, Normalization and Expectation, Preserving Probability Over Time. We have finally arrived at the last pieces of the puzzle, proving that this corrected probability behaves itself permanently as time ticks forward. The overarching takeaway for us here is that because the total probability of finding the particles somewhere, anywhere in the universe, is exactly 1, the state function preserves its normalization over the entire course of time development. Basically, once it's normalized, it stays normalized. And this is absolutely critical, because calculating the expectation value, which gives us the average physical outcome of an operator, strictly requires the wave function to be flawlessly normalized from the start. We can see exactly how this normalization integral is mathematically formalized across all volume space. This bedrock of stability allows us to accurately predict physical realities using the expectation value of any operator A. Because Dirac fixed the foundational math to prevent negative probabilities, the predictions we make about reality using these tools remain rock-solid and accurate. So Dirac brilliantly solved the crisis of negative probability by inventing those bizarre 4x4 alpha and beta matrices. But, as you might guess, in the world of quantum mechanics, solving one problem just creates another. Those mysterious matrices open the door to entirely new, mind-bending physics. By fixing the math, his equations ultimately predicted particles with negative energy states, literally laying the mathematical foundation for antimatter. Dirac fixed one massive problem, only to leave us staring at even more incredible mysteries in the quantum realm. Just amazing.
Thank you, students, for watching the video session. We have successfully navigated the foundational Klein-Gordon and Diractions, mastering their covariant forms, intricate matchings of probability density. Please stay tuned for our next chapter in Advanced Quantum Mechanics, where we will continue to uncover the profound mysteries of the quantum realm.